All right. Hey, everyone. Thanks for stopping by today. I know transportation has been a little bit difficult, for some more so than others. But we will be having a meeting today, and today we're going to be talking about an introduction to neural networks. And I want to say, I'll address this probably at the end of the meeting today. But first of all, I want to address that this will be covered again, possibly not with the same slide set, possibly not with the same presentation, but the concepts and ideas covered in this meeting will be covered again at the first meeting of winter quarter. And we're doing this because A, the strikes are happening, so we know people might not be able to make it. And B, we thought that neural networks are kind of one of the most important things in AI, at least right now. And I feel like based on the way we have things structured, it's unfortunate that we don't get to them until winter quarter. So I'd like to get you guys into them as soon as possible, and then we'll be covering it again at the beginning of winter quarter because more people will be showing up, and we want to get them the introduction before we dive right into everything else. So with that being said, let's go ahead and start with a little bit. Whoop, hello. This is frozen. Sorry about this. Hello, welcome in. Okay, there we go. Let's go ahead and start. And let me just ask, some of you may know what a neural network is. Some of you may not, and that's okay. But first, what comes to mind when you hear a neural network? There's no such thing as a wrong answer. But go ahead and raise your hand. These are some things to get you kind of brains turning. Yeah. A machine learning network with more layers. Yeah, we will be getting into that a lot more. So layers we'll talk about in today's presentation, and machine learning, as we've talked about, as a distinction from artificial intelligence, is when it comes up with the rules that it uses itself. So these are not predefined rules. It is learning and figuring out the rules to make decisions on its own. So yeah, very good. Any other ideas? Okay, cool. So the first thing that we will do is we will review perceptrons, because perceptrons, as I mentioned during the lecture, we covered them, are the basic building blocks for a neural network. A neural network is essentially just a bunch of perceptrons. So to talk about a neural network, first, let's talk about the perceptron. We have as labeled here our inputs. So these are what the perceptron takes in. So this is generally numbers of some kind of value, and you have some number of them. So this one we see takes in 3 inputs. This could be like 5, this could be 2, this could be 7.8, et cetera, whatever you want them to be. Can anyone tell me what these are? Yeah? These are weights, correct. So each of these inputs are going to be multiplied by a weight. So we have our x1 here that I said was 5. It's going to be multiplied by this weight. Let's say this weight is 8. That's going to become 40. If this input I think I said was 2, then it would be multiplied by this weight of 1.5. That would get us to 3. And then this was like I think I said 8.7. Let's say this weight was 10. That would get us to 87. And then this symbol is the summation symbol, and it means we add them all up. So we're going to take each of the inputs multiplied by a given weight and add them all up. And then we're going to add in this term. Does anyone know what that term is? No? Bias, that is correct. So we have our bias term, and this is just, you can think of as another weight that instead of being multiplied by a input is simply just added. So if this is 5, we're going to take this summation of all the weights and inputs and add 5 to it. Or if this is 70, we're going to add 70 to it. Or -7, we add -7 to it, et cetera, et cetera, et cetera. So I think we understand our perceptron. Does anyone have any questions before we move on and talk about what we're going to do with it? No? Okay, perfect. So let's talk a little bit about the limitations. Ignore this bullet point. These were slides that were adapted, and I forgot to remove it. And that bullet point, actually. So I guess for now, we're just going to talk about this bullet point here. And that is the limitation is that perceptrons can only model linear functions. I want us to take a look at these two graphs here. And I want us to think about a linear function. What can a linear function draw? If we're going to draw a linear function, what does it look like? A line, exactly. So let's say the goal is to predict red or green. That is what the perceptron is trying to do. And remember, the perceptron can only use linear functions, or a linear function. That's important. A single linear function, and that is going to be a line. So can anyone tell me how, let's say we talk about this image first, we separate all the green dots from all the red dots with a line? No ideas? How do we separate these green dots and these red dots? So classify them. So that's what the perceptron is going to be doing with a line. Well, you could use more coordinates, but then these would be on more coordinates. So this is just looking at 2D inputs. No ideas? Okay, what about this one? How do we separate this with a line? Can we like angle it? It's a bit of a trick question. You can't. These are not linearly separable, which means that a perceptron cannot separate this data. That would be the same if the data was curved. That would be the same if the data was anything like this. You can't do it with a line unless it's just what you need is two distinct groups, one on each side, and that way you can separate it with a line. But most things that we're trying to classify and do don't look like that. That's not how they work, and therefore a perceptron doesn't work very well. So what do we do? What if we combine them? What if we combine the perceptrons? But in order to do that, I'm going to first simplify a perceptron because we're going to have multiple of them and it's going to start getting really confusing if we use this representation every single time we want to talk about a perceptron. So instead, we are going to call it a node. A perceptron is now a node. Perceptron node, perceptron node, perceptron node. Those terms should be interlocked in your brain right now. No ability to separate them. That's what a perceptron is. So again, we have some inputs. It's going to get an output, and we are going to call it a node. Does anyone have any questions about this slide? Okay, perfect. So now that we have simplified, this is what our perceptron is going to look like now. We have our three inputs and we have our node. So this is an abstraction of all of the perceptron into this circle with a letter N. Any circle with the letter N here is going to be a node and therefore a perceptron. Perfect. Thank you. Okay. So how would we add more perceptrons? How would we add more nodes? Does anyone have any ideas off the bat? Would we do them in sequence? Would we do them in parallel? Would we do one input for each perceptron? Would we do two inputs for one perceptron and one for the other? What would we do? Yeah. Okay. So stack them in parallel. Yeah, that's perfect. That's what we're going to do. We're going to have a bunch of them stacked in parallel, and they're all going to take the inputs at the same time. So how would we draw the lines for this? Remember, a line going from an input into a node or perceptron is what we described in the perceptron image. It's that input being taken by the perceptron. How do we draw the lines? Let's talk about first for node 1. How do we draw the lines for this perceptron? Does anyone have any ideas? Yeah. Yes, connect each input into node 1. So we're going to have this input, draw a line there, this input, draw a line there, this input, draw a line there. And it's going to look exactly like this. All of the inputs going into node 1. What about node 2? You can shout it out. Same thing. Yes, all the inputs going into node 2. What about node 3? The exact same thing. Yes. Okay. Now let's draw it all out together. So we have all the inputs going into node 1. We have all the inputs going into node 2. And we have, all the inputs going into node 3. Does anyone have any questions about this? Perfect. So each of these perceptrons gives an output. Let's say this one gives an output of 3, this one gives an output of 7.2, and this one gives an output of negative 1.2. I have a quick question. Can anyone tell me why these can give different outputs despite all taking the same input? Yes. Can you clarify? Different weights, different biases. So they're all taking the same inputs. So if we go all the way back to this one, they're all taking the same inputs, but the weights and the bias can be completely different, therefore giving different outputs for them. So we have each of them giving an output. What can we do with now what? We have three outputs. What can we do now with those outputs? We have three numbers. Yeah. NAND gate. Yeah. So what if we use another perceptron? That's another way we can combine them. Remember, a perceptron takes in three things, three inputs. Those inputs don't necessarily need to be the ones that were predefined. They can be any numbers. So this time we're just going to use the three outputs of this thing we've created as the inputs for the next perceptron. Does that make sense to everyone? Okay, cool, perfect. So let's remember this is what we started with, and this is where we're at. But let's specifically look at what we started with. What did we do? What did we do from here? What was the first step we took? Yes, but for each perceptron, the first thing we did was split this into three different perceptrons. So what could we do here? That goes into what? That goes, yes, that is what we're doing. But what could we do? Remembering this step that we took. What could we do here? Yeah. Yes, split this into more perceptrons. So this perceptron that we just added, instead of one perceptron, we're going to have more perceptrons. So again, if you remember, what we did is we took one perceptron, and instead of one perceptron, we simply added two more and made all of the inputs go into each of them. Does that make sense? And if not, do you guys have any questions? Well, we'll talk about that, but that's a decision that you can make. You can say, I'm going to stop here and not do this anymore. But the point I wanted to make is that you can do this. You can keep doing this. You can take a perceptron and split it into multiple and have just the inputs go into more perceptrons. But that's a very good question. We'll get to that, I think, in 2 slides. Does that make sense? How we can just keep adding? So why stop there? We can keep adding layers and layers of perceptron. Oh, we have our inputs. Let's put them into 3 perceptrons. And then we have these outputs. Let's call them inputs and put them into 3 more perceptrons. Now we have 3 more outputs, call them inputs, 3 more perceptrons, more perceptrons, more perceptrons, more perceptrons. Now, remember, all they're doing is each perceptron is taking all of the previous outputs as inputs. We could have more perceptrons per layer. We could have, or per block. We could have 4 perceptrons, and this 4th perceptron would just take in 1, 2, 3, and then it would pass in to all of these ones. So this is called a multi-layer perceptron, also known as a neural network. Now you guys know what neural networks are and how they work a little bit. Let's go a little bit deeper. So I've said layers, but I haven't really explained what they are. Let's think about a cake. This cake has layers. It has 1 layer. It has 2 layer. It has 3 layers. That makes sense? So let's turn it on its side. Okay, that's a little unfortunate. But we are going to look at these layers as the vertical stacks of perceptrons or nodes. So a single stack of perceptrons is a layer. This would be the first layer. This would be the second, and this would be the third. Just kind of terminology, what we mean when we say layers. Now, as you were saying, what's our output? What's this final thing? Our output can be whatever we want. Let's say you want a single number as your output. Well, then the final layer would simply be 1 node. If you want two numbers as your output, you have the final layer be two nodes. If you want three numbers as your output, it's three nodes, five numbers, five nodes, et cetera, et cetera, et cetera. If you want to get an output of 1,000 numbers, let's say you're trying to predict 1,000 different things, you simply put 1,000 nodes at the end of your network. That is how we determine the output, and we have a certain number of layers, and then the final number of nodes or the final layer's number of nodes is how many outputs we have. So, why did we do this? It's because we wanted to make more complex functions. So for this, you would still just have one output, and the output would essentially classify something as green or red. And it would still, the final output would still look like this. But that doesn't change anything. We're still taking in three inputs all the way over here and then getting one output. So why did we do all of this? Well, it's because when you do this, it can actually model more complex functions. It has more kind of built on top of it. But there is unfortunately a problem. And that is that linear functions will collapse. So if you combine linear functions like this, they will collapse. If you have a linear function of another linear function of another linear function, it will collapse down into one linear function. And what did we just talk about that we can't do with a linear function? Yes, we can't accurately model this data. So what do? We need to add some kind of non-linearity. And that nonlinearity is going to be in the form of activation functions. All activation function means is a nonlinear function. So these are going to exist in between the layers. Let's think about for now the layers as a function. So this layer is a function, this layer is a function, and this layer is a function. And each of these functions are going to be each of these functions are going to be linear functions. And so as we talked about, they would end up collapsing to one function because that is a property of linear functions. I'm not going to explain why. We'll probably go into that in a later meeting, but just know that linear functions composed will collapse. So what do? We are going to add activation functions between the layers. What does this look like? So we're going to first split apart the layers. And then we are going to shove an activation function in there. So the output of this node, instead of going right into this node, and this node, first is going to go through an activation function. And it's going to be converted from a certain number to another number. And the important part is that conversion is nonlinear and therefore an activation function. And the same here. So each of these are going to be passed through an activation function before reaching the next layer. And this can be thought of mathematically like this. So instead of f of g of h of x, where each of these are the linear functions or the layers, we have f of nonlinear of g of nonlinear of h of x. So we can no longer collapse them into that q of x, that other nonlinear function, because it's no longer a composition of linear functions. So again, looking at this diagram, we have a linear function of a nonlinear function, of a linear function, of a nonlinear function, of a linear function. Just make sure between every linear function, there's an activation function, a nonlinearity. Otherwise, those two functions would collapse into one. So let's think about some activation functions. Can someone give me examples of some nonlinear functions? What's a function that doesn't give a line? Exponential. E to the x. Sure, that is not a line. What about another? What's a function that when you graph it is not a line? Any function. X squared. Perfect. That doesn't give a line. Yeah, this is an example of an activation function. What's another one? X cubed. Perfect. This is also an activation function. It adds some kind of nonlinearity. What about another one? Square root x, perfect. That's also you can use that to add nonlinearity. Okay, I think we've got some ideas. So let's take a look at these two that we have right here. There is a problem with these two. I don't expect you guys to notice it immediately, but can anyone have a guess? Mm-hmm. That is a good guess, but I will remind you that we have these linear functions and then nonlinear and then linear and then nonlinear, and that is how it can model any arbitrary functions. So that is a good guess, and it might make it more difficult, but there are some rules that say if you expand it and have a bunch of these layers, it can model any arbitrary function, including spirals or a circle. Any other guesses? So let's see what happens when we put in 2 for x squared. What do we get out? 4, exactly. What happens if we put in 5 for x squared? 25. What happens if we put in 100? 10,000. Yes. What about 1,000? 1 million. Yeah. So we put in a number and we get a number that is way bigger. It is just huge compared to the original number. And what this ends up doing is it would make the numbers explode. So by the end layer, you would be getting numbers of like 5 trillion, 8 trillion. And these are really difficult for the computer to deal with and make other things just stop working as well. We don't like these huge numbers. And the same thing happens for x cubed, except it's even worse. 5 gives you 125, 2 gives you 8, 1,000 gives you 1 billion. So these aren't great. So let's take a look at a couple other options. The first thing is sine of x. And this is actually a pretty decent option. One thing to note is that there are a lot of repeats. It is cyclical, so that makes it a little bit difficult and can cause some information overlap. If you think about like basically putting in 0 gives you the same thing as putting through pi, so it basically collapses those 2 items down to 1 item. So that's not great, but it doesn't have the explosive issues that these two have. So let's look at another. Sigmoid. This is quite similar to sine of x, where it collapses it from it can be huge to now it's just giving an output of between 1 and -1. Except sigmoid doesn't have this cyclical property. Essentially, 1 is an asymptote and -1 is an asymptote, and as it gets higher numbers, these are weird. Please ignore these. This is a bad image, but this is 0, 1, 2, 3, -1, -2, -3. I don't know why those numbers are like that. But yeah, so it's going to asymptotically approach 1, asymptotically approach -1. And this basically says that any number that any input that's bigger than a different input, the output will also be bigger. Same with if you put a smaller input in, if you put an input that's smaller than a different input, the output will also be smaller. So it keeps that balance. But what it does is it holds it between 1 and -1. This is the sigmoid function. I think it's 1 over e to the -x. Is that correct? Thank you. 1 over 1 plus e to the -x. That's not important. The important part is that it generates this graph. And I just explained why graphically that graph is nice. So let's talk about another one. We have ReLU. ReLU is special. It's basically an if statement. If the number is less than 0, the output is 0. If the number is greater than 0, the output is the same. Or if the input is greater than 0, the output is the same. So basically it says, is my input less than 0? If so, return 0, else return the same thing. Why is this nice? Why is this good? Why is this helpful? Why might this be one of the most popularly used activation functions in all of machine learning? Sure, it can help keep things positive. More importantly, it's easy to calculate. How difficult do you think it is for a computer to calculate 1 over 1 plus e to the negative x? Relatively complicated. What about an if statement? How complicated is it for a computer to calculate an if statement? The answer is not that difficult. It can do them very, very easily. You and I, we all like if statements. Computers like them even more. And so that's why we use this, because it's super fast, it's super easy, and it does add nonlinearity. This is no longer aligned, so it satisfies the requirements for an activation function, and it's really easy for the computer to calculate, so we use it. And I will note that ReLU and sigmoid are the only activation, or out of these 5, the only activation functions that people really use. There's a couple more. There's tanh, which is something else. But mainly you'll end up seeing these a lot, and specifically ReLU. ReLU is like 90% of activation functions are going to be ReLU. Sigmoid and some other ones like tanh come up other places, and I can explain why and when to use those at another point. But for now, this is the important stuff. So now that we've covered activation functions, we've covered how a neural network is built out of a bunch of different perceptrons. You have your inputs. We talked about how to decide your output based on just the number of neurons in the last layer. Why activation functions are important, because they add nonlinearity and stopping the neural network from collapsing, and what they are and how they work a little bit. They're just functions. So let's talk a little bit about loss. The output of a neural network is going to be some kind of numbers, and we need to measure how bad it is in order to improve it. So loss is going to be a representation of how bad our model did. The goal is to make the loss as small as possible. So we need something to basically say, hey, if the model did really, really bad, we want the loss to be high. If it did really, really well, we want it to be low. So we are going to use loss functions for this. So I'm going to give us just an example of a comparison of two arrays. This first array is what the neural network predicted. The second one is the actual values that we trained on. Remember, for training, neural networks are a supervised learning, which means we need actual outputs and correct answers to train it on. So these are the actual outputs and correct answers. And then these would be the output of the neural network. Which of these two is number 1 or number 2? I guess I have is number 1 or number 2 better? Is it a better prediction? Which is a better prediction that the neural network made? Let's say we have 2 neural networks. One got the actual values of 1 and predicted 1. The other got the actual values of 2 and predicted 2. Which is better? Just looking at it. Sure. Sure. Can you tell me why? Right. And then also 5.2 is pretty close to 4.5. 1 is very close to 2 compared to over here. 1 and 8 are very different. 32 and 87 and 8.7 are very different, and 9 and 35 are very different. We just looked at those and said, oh, these numbers are the same. These numbers are different. We need a way to actually measure this. Now we're going to use mean squared error. I know we've talked about this a little bit in a previous lecture. I think it was the perceptron lecture, but I'm going to go over it again because I think it's a very important thing to understand. So mean squared error. This is going to do exactly what it says it's going to do, except in the reverse order. But let's take a look. What does mean mean? What do I say? What do I mean when I say the mean? You can raise your hand. You can shout it out. Average. Perfect. Okay. Squared. That's going to be multiplied by itself. And error. That's the difference or subtraction. So when we say error, we're talking about taking 2 numbers, subtracting, and finding the difference between them. Does that all make sense? Great. Okay, so now we just follow these steps. First error, then squared, and then mean, and we get the mean squared error function. It's actually quite self-explanatory, but let's go through it manually. So first, the error. We're going to say 1 minus 2 is -1, and then 5.2 minus 4.5. Let's do this. 1 minus 2 is -1. 5.2 minus 4.5 is negative 0.7. 3 minus 3 is 0. 2 minus 2 is 0. What is 1 minus 8? -7. What is 32 minus 8.7? I'll just give it to you guys. Yes. And what is 9 minus 35? -26. So, yeah, those were not easily to do in your head, but good job on the 23.3. So we have our error. These are the differences. These are simply subtracting one array from the other. Now we need to do step 2, squared. What is -1 squared? What about 0.7? Almost. It's going to end up being 0.49. What about 0 squared? 0. What about 0 squared? What about -7 squared? 49. 23.3 squared, I'm not going to make you guys do that in your head. -26 squared, I'm not going to make you guys do that in your head, but this is what they come out to. So over here we have 1, 0.49, 0, 0. And over here we have 49, 542.89, and 676. Let's take the last step, step 3, average. How do we take the average of something? Exactly. So we're going to sum this up. That's going to be 1.49 divided by 4. It's going to be 0.37. And over here, we have 4.9 or 49 plus 542.89 plus 676. And all that added up is going to be 1,267.89. We divide that by 3 and we get 422.63. So if you remember back at the beginning, we said 1 is a lot better because the predictions are more similar to the actual values. 2 is a lot worse. Now we can quantify exactly how much better and how much worse they are. 1 got a mean squared error value of 0.373. That's a very small number, at least compared to the mean squared error value that 2 got, which is 422.63. So it would seem that the mean squared error function agrees with us that this one, that predictions 2 and actual values 2, is much worse than our predictions 1 compared to actual values 1. This is good. This is how the mean squared error function works. Let's look at a couple of others. First, mean absolute error. This is like mean squared error, except remember that squared step. Instead, we're just going to take the absolute value. Simple, just change step 2 in your head. We also have another set of functions called cross entropy. These are for when instead of predicting a number, you are trying to predict the correct class. Say, is this dog, cat, or bird? Or maybe it's only 2 things. It's yes or no. It's predictions like these. So if there are 2 options, if you're trying to predict like yes or no, you have binary cross entropy. And if you're trying to predict any more than 2 options, cat, dog, bird, multi-class cross entropy. Cross entropy means you are choosing the correct options. It's for classification. And then, of course, we have good old mean squared error. So cross entropy functions for like when you're choosing your class, and then the mean absolute error or mean squared error for if you're choosing kind of trying to get a specific number. These are 4 of the most popular ones. There's more out there. There's a bunch of ones that you can use in different settings, but these are the main ones that generally kind of people use most frequently. So let's do a quick recap. First, we talked about layers and how we could combine perceptrons, calling them nodes, into different layers. And then we combined all of those layers into a neural network and how we pass through every input into every, pass through every output into every input of the next layer. So every node is connected with every node in the layer after it. This is called fully connected. The term is fairly self-explanatory. It's fully connected because every node is fully connected to every node after it. And we talked about how that brought us to multi-layer perceptrons, or MLPs, aka neural networks. And we also talked about, I need to change this. These slides were adapted. I'll talk about that in a second. Into the activation functions that we use to stop them from collapsing. So now we have neural networks are stacks of perceptrons, and in between each stack of perceptron is a nonlinear function. And then we also talked about how the output was determined by the number of layers in the final, the number of nodes in the final layer. And then we talked a little bit about loss and how we measure how good a perceptron is doing. Any questions?
You go back to the multi-class process results, like, yeah, I've heard sometimes people use this thing called softmax. Is that also multi-class cross entropy?
So softmax, essentially what it does is, actually, do you want to talk about it?
I don't.
Oh, you're okay. That's a leading question. I see. So if I remember correctly, softmax is at the end of your network. You have a certain number of outputs, and these outputs are going to be numbers. But we want to convert this into some kind of classification choosing. Softmax is for when you want to do a classification, but our outputs are a bunch of numbers. How do we do this? Well, what we do is we set the number of outputs or the number of nodes in the final layer to be the number of outputs that we have. So if we're trying to classify cat, dog, bird, the number of final layer nodes will be 3. 1 for cat, 1 for dog, 1 for bird. And then what we're going to do is softmax, essentially, I think it's so there's a process and there's one step that you don't necessarily go through, but what you're eventually going to do is have a layer that literally looks for those and sets and chooses which one is the highest. So it's like a probability prediction. What the network ends up learning is one node is how sure it is it's a cat, one node is how sure it is a bird, one node is how sure it is that it's a dog. And then what it's going to do finally to get the classification is choose which is higher, and that is going to be the output. What you can also do is the layer before that, you can basically normalize it. So you're going to say these one add up to 1, and it's just a simple function. You have a bunch of numbers, you want them to add up to 1, but have the same ratios. That's a very simple function. You divide by the total. And what that does is it means that layer before the final output, you can look at it, and that is the exact percentage sure that is a dog. So let's say the neural network has a bunch of outputs. You put this normalization thing, and then instead of a bunch of numbers representing surety, it'll say I am 80% sure it's a dog, 10% sure it's a cat, and 10% sure it's a bird. And then it'll choose 80% and say my prediction is dog. And then softmax, I think, is the layer that converts it from a bunch of numbers to probabilities. But yeah, that's what softmax is. Any other questions? Cool. Okay. Yeah, I think this is the last slide. Thank you guys for coming. Yeah, this was a bit of a different meeting. This was actually from a class that Eric's sitting over there. Eric, myself, and Anthony. So if any of you guys go to the Sky's No Limit workshops, Anthony is the one running those. We are going to be teaching a class next quarter called CMPM 17. And essentially, it's going to be teaching about neural networks, machine learning, and stuff like that. In this club, we approach everything from an AI perspective. In this club, we talk about everything from an AI perspective. In the class, we talk about things from a machine learning perspective, and it's a lot more application focused. These club meetings are very theory based. In the class, we will go through kind of a little bit of the theory, but we'll go a lot more into the application. How do we actually do things? This slide set was actually pulled from a day of the class. So if this was interesting to you, if you're still confused about neural networks and then also want to get a PR gen ed out of the way, you can go ahead and take our class. It's CMPM 17 section 2. If you scroll down, not the description, but the other block of text will talk about AI and machine learning. There was also a post about it in the Baskin Engineering newsletter, if any of you guys are following that. But yeah, so just wanted to advertise that a little bit. If any of you guys are interested in it, we will end up going over some of the stuff covered in this club a little bit, but it is aimed, just like the club, to be accessible to anyone regardless of where they're coming from. So you might find a little bit of repetition, but for the most part, it should hopefully be new ideas or at least a new angle for current ideas. So yeah, I wanted to put that out there in case anyone was interested. And yeah, I know we're ending a little bit early, but yeah. Thank you guys for coming. If you're not on the Discord or Instagram, contact me. I forgot to put the end slide here. But yeah, thank you guys so much.